So here's an optimization problem similar to the ones that we hit on in the quadratic section, but we're going to attack them in the same way, even though the formula we're going to come up with is going to look different. It's not going to be a quadratic. Anyways, our focus is going to be about volume. And of course, in order to figure out the volume, we need to label the size. We have a width. We know that the width, oh, look, it looks like I have a grammatical error. There, I feel a lot better there, other than my bad handwriting. The length is 3 more than the width, and then of course I don't know what the height is, so I'm going to call it h. And my focus is the volume. The width times the length, w plus 3 times the height. But that has 2 variables, so we need to go find a constraint, and that's going to come from this $300 here. All right, well, that $300 is going to be the cost of all 5 sides. So we have the area of the bottom, and that's $5, so I'm going to multiply it by 5, right? That's this area down here on the bottom. And then we have 2 of these sides, that side and then this side. And each of those sides costs $3, and there's 2 of those sides. And lastly, we have the front and the back. That's W plus 3 times H. That costs $3, and there's 2 of them because of the front and the back. We simplify that, and we end up with this equation. It's got a W squared in it and an H squared. It turns out that because of that, H is the easiest one to solve for. It honestly doesn't matter which one we solve for, but H is easiest, so we're going to do that. Go ahead and factor the H out and move the 5W squared over to the other side. And when we solve for H, we end up with this lovely equation. So let's go back to our focus. So our focus was this volume. We now know what H is, so what we're going to do is we're going to take this and plug it in to our focus. And we have this new formula, which is a rational function, right? It's got a denominator down here. So we're going to go ahead and graph it on the graphing calculator. I graphed it so that x goes up to 10 and starts at 0. Of course, I'm not going to look at any negative x's. They don't make any sense. And I think I might have gone up to, I'm not exactly sure, 80 or 90, something like that. Anyways, the key thing is the maximum happens when x is about 4.11, and in my calculator, x and w are going to be the same thing. So to get the maximum value, the width is 4.11 feet. The length is 3 more than that. Remember, it's 3 more feet than the width, 7.11 feet, and then you just have to plug that into the height equation, and that gives you about 2.45 feet, and you're done with the problem.